All right, thank you again for inviting me to speak. So the topic is basically to report on the studies of galactic sources with VERITAS. Okay, and what I thought we would do is, instead of me talking about VERITAS and galactic sources, I thought it would be helpful if people in my group who are also experts in analyzing data with VERITAS, I thought it would be better if they spoke about the work that they're doing. So the format is I will speak a little just as an introduction, just to set up the field, and then say a little bit about the overall program of galactic science in VERITAS. And then I will move to Ro Shang and Juyan Wu. And on the screen, you can see Ro Yushang, who is a postdoctoral scholar at Barnard College and Columbia University. And he has actually a lot of experience working on galactic physics, on VERITAS detection of galactic sources. And he also comes from UCLA, from his previous position, where he was an expert on the Schwarzschild-Curie telescope. So he was doing a lot of instrumentation and basically with the optics of the telescope. So right now, Ro is also the convener, one of the co-chairs of the Galactic Science Working Group within VERITAS. So he's not only responsible for his own work, but he's also running the whole thing, the whole Galactic Science program. And so Ro will tell us about an unidentified Milagro source, Milagro J 1908+06, which we then followed up with VERITAS, HAWK, and Fermi. And we have a paper that just, Ro was one of the leading authors, and he'll present on that. And Juyan Wu, who you also see on the screen, actually behind her is the four VERITAS telescopes. So that's a great introduction, because that's the site in Arizona. So Juyan is actually in her final year of her PhD. So very imminently next year, early spring, she will be defending. And her work is basically on TeV observations of galactic sources, and particularly sources like CAS-A, as well as LASSO sources, unidentified LASSO sources, which are PeVatron candidates. So we were all very excited by these results from LASSO. So that's one of the topics for her thesis. But the other thing that she brings in, which is kind of unique for us, is she brings in all of the X-ray expertise, because she works with people in the New Star group, Kaya Mori, Chuck Haley, and others. And so her thesis is connecting the X-ray to the TeV. So this is kind of like a very quick introduction. And maybe I will just start by introducing. And so I'm going to share my screen. And if people on Zoom cannot hear me clearly, please let me know, okay? Let's see if this works. Okay, so you should be able to see my slides now. Okay, and what I will do is, I'm not going to give, so the idea is that so we have like 45 minutes. It'd be nice to have a discussion. We have an hour. If you interrupt me, that would be great. So we can have a discussion as we speak, or we all finish speaking and then you ask questions. Okay, so I think that overall the three of us will not speak more than 45 minutes. Okay, so we do 20 minutes, 15, maybe Juyan has 10. So we do it like that. So I think I'll give a little bit of an introduction, only because not everybody was at the colloquium. How many people were not at the colloquium? Okay, just a few. That's the one not here. But maybe I give just a quick introduction on why we are studying these cosmic galactic sources. And one of the main motivations is understanding the highest energy cosmic rays. And as you know, this is basically more than 100-year-old mystery at this point. What you're seeing here is the energy spectrum of cosmic rays. You can see the E squared D and DE as a function of logarithmic energy on the x-axis. So it's on log scale on the x-axis. You can see this is several decades in energy. So it basically goes from more than 12 orders in energy. This is in GeV per particle. So really like 20 orders of magnitude in electron volt scale. And just for comparison, you can see where is the LHC, where is the TeVatron. So these particles are accelerated in sites that we cannot on Earth replicate. So these are really powerful sources. And the spectrum itself, there's a lot of information. We know what the energy density is. We know somewhat the composition. We know that supernova remnants can produce enough power in a single explosion in the galaxy to power these sources. But if you look at the spectrum, there's a lot of interesting features, including what is called the SNE here, SNE feature. where the spectrum changes. And we think that basically for the highest energy, the very highest energies, these are extragalactic. The galactic cosmic rays are somewhere here, but the knee region, how do you accelerate particles up to the knee is still a mystery. So these are some of the reasons why we are interested in these galactic sources. Okay, and then very briefly, we also said that, and some of this was again covered in my talk, which I won't go into too much of the general background material, but it is important to mention that for understanding the sites of cosmic ray acceleration, you really need to look at neutral messengers, because the Milky Way, the galactic fields in the Milky Way will scramble the directions of the charged particles coming from cosmic accelerators. And so if you're only looking at cosmic particles, you won't know what direction they were pointing back to just by measuring the cosmic particles. So you really need, at the same size, you need to rely on the fact that there could be neutrinos produced in hadronic processes, that these sites also produce gamma ray emission. And so if you look for neutral messengers, you have a better way and better chance of studying these sources. And in fact, we know that there is a diffuse gamma ray emission due to cosmic rays. Recently, IceCube also published a neutrino diffuse sky map, which shows several sources, I mean, not several sources, but several hotspots that are associated with neutrino sources, high energy neutrinos, which could be interesting for following up. So that's the overall goal. And then the other big thing that kind of, I was taken away by surprise, and that was the LASSO results. So here what you see is the ultra high energy sky. I was measured by LASSO, which is this extended large field of view detector. And you can see this is basically after 933 days of data. 43 of these sources are ultra high energy, basically above 100 TeV. And these are different classes of sources. There's pulsar wind nebulae, there's young massive star clusters, supernova remnants, microquasars. So these are sources where particles are accelerated. And these are prime candidates for PeVatrons or PeV accelerators. So this is kind of the overall motivation for the field. And I think we all know the instruments, so I will skip the instruments that are currently working and just mention that we do rely on the synergy between these instruments because they offer different advantages and disadvantages. So while we rely on detectors such as LASSO and HAWK for full sky coverage and serendipitous observations and sky surveys, and that's really great, we really need the Cherenkov telescopes to zoom in and pinpoint and follow up these observations with much more precision and better angular resolution, better sensitivity, and basically for morphology studies, these are much better. So you do need to rely on the connection between these wide field instruments such as LASSO and the Cherenkov telescopes such as MAGIC, VERITAS, and HESS, as well as Fermi, which provides you information on the spectrum on the lower energy part. So you need all of these instruments together in order to study these sources. So since everybody here is from the background of Cherenkov telescopes, I'm going to skip the technique, which I think we all know how these work. If there are questions about this later, we can discuss it. But the idea is that these instruments indirectly measure radiation by looking at the Cherenkov radiation, which is kind of like a fallout as a result of an incident gamma ray that hits the atmosphere and creates an extensive air shower. And the technique is basically to measure these fast Cherenkov light pulses and then do imaging. And this has become now a very established technique. CTA is coming up and should do this much better. And then I just wanted to introduce the VERITAS group because we are a small collaboration and about 50% of us are early career scientists working on several of these topics. Okay, so let me then just come into the galactic sources and then just mention the fact that if you look at the TeV catalog currently, so this is from TEFCAT, which I think many people have used it, but it's a resource, it's an online catalog that you can go in and you'll see basically all of the TeV sources that have been detected to date. And in fact, if you spend time with the catalog, you can actually pinpoint on each one of these sources, you will get a whole history of the detection of the source, the characteristics of the source, and so on. And so what you see here is basically all of the TV sources that have been detected today. The galactic sources, which is the focus of this talk, is basically along this galactic plane. So this is a projection where the Milky Way galaxy is along the plane, and you can see here all of this red sort of diffuse emission behind these point sources is basically cosmic ray interactions in the Milky Way galaxy. So these are diffuse gamma rays. This is not from the TeV catalogs, it's actually from the Fermi-LAT satellite experiment. And so Fermi measures this diffuse emission. So there's a lot of sources, a lot of emission that's coming from the plane itself. And several of these sources overlaid on this, you will see all of these gray circles, as well as some of these pink and green. These are the different kinds of galactic sources that are detected in our own galaxy. And these can be supernova remnants, supernova products, pulsar wind nebulae, TeV halos. It can be things like binary systems, microquasars. It can be things like molecular clouds, giant molecular clouds, the Crab pulsar, and so on. And most interesting or most intriguing, I would say, are these unidentified sources. Sometimes these are called dark accelerators because people have been looking to find what are the counterparts and not been able to find them. Or, maybe we just don't have sufficient information. Maybe there are too many counterparts and we just don't know which one is the correct one. So whatever, the gray ones are basically unidentified in the sense that we know they exist because we measure their spectrum and energy and flux and position in gamma rays and morphology, but we don't know what they are. Okay, so that's one of the goals. So what does VERITAS do? VERITAS has actually had a long program of, yeah, go ahead. Question?
Here are the points for gamma ray sky 300 sources, and before you have presented the gamma ray diffuse map.
Yes.
In the diffuse map, I can identify as the beautiful star-forming regions of the Scarpe Centaurus,
yes,
all the region of Orion, and so on. So why in this galactic gamma ray sky are all in the plane? They are not located as it was the diffuse gamma ray sources material in Escocen or in Scorpio. It's because you have very few particles, or it's because there is no you do not expect in Scorpio Centaurus, for example, a star-forming region very active, a lot of supernovas exploding, blah blah blah. You do not expect.
We do expect gamma point sources from the star forming. So the question is, yes, yeah. So the question is, you see this, as I understand that this is a diffuse emission map from Fermi, and you can see diffuse emission all along the plane, and you can see a little bit off the plane, like here. Those are actually the bubbles, the Fermi bubbles, which could be some kind of emission that is powered by the black hole at the center of the galaxy. I mean, or by the pulsar wind nebula that's ejecting these particles. But anything off the plane, like all of this dark blue, that is also diffuse emission, but it's extragalactic diffuse emission. It's not coming from our galaxy. In this projection, the galaxy is basically plus minus 5 degrees, or plus minus 10 degrees maybe. Like all of this red emission is from the galaxy. And the yellow emission is the strongest, the red is a little bit less, and blue is a little bit less. The blue is an order of magnitude less. In fact, I don't have the scale here, but all of this blue emission is extragalactic. And it is diffuse, and we do measure it. And most likely, these are unresolved point sources. But I'm not talking about that in this talk. In this talk, I'll only focus on the red and the yellow. And yes, there's a lot of diffuse emission, and some of that is star-forming regions, like the Cygnus region. And there we do see some sources. Yes, exactly. And there are some point sources in there, and there are some sources that maybe they are unidentified and associated with them. But there is loosely speaking, there's a lot of fuzziness here that we are trying to follow up. Okay, and in fact, Julian and Ro will mention some of this later on. So, but if I come back to the catalog, I'm just going to focus on a few sources today, because there is a lot of gray here and the greens, which are the subject of the talk, but none of the reds. All of these reds are extragalactic sources that are active galaxies and blazars, and they're black holes, and we understand them, but not today, okay? So only the galactic sources, these are the sources that VERITAS has detected. This is kind of like a table and a list, and it's not so interesting, but I'm just going to keep it here in case someone wants to look at it later on. But you'll see that the categories of sources include supernova remnants, they include pulsar wind nebulae. There's several of them that HESS has detected. In some cases, MAGIC has detected. So we know these are well studied. Okay? For example, the 3 northern supernova remnants, these are the famous ones. These are the historic ones like Cassia, Tycho, and IC443. They have been well studied previously in X-rays and other missions. But now, with MAGIC and with VERITAS, we have much better, precise information. So in addition, we also have gamma ray binaries. Several of them have been detected. Unidentified sources. Pulsars. In the Crab pulsar, the detection of pulsed emission at TeV energies from Crab pulsar by MAGIC, by VERITAS, and also pulsed emission by HESS of the Vela pulsar. These were kind of like some of the highlight results from the TeV instruments. It's kind of unexpected. Okay, so what do we do? So today, we won't have very much time, so we can always discuss later. We are interested in the quest for PeVatrons, and so one of the questions that we had starting out very early are supernova remnants PeVatrons. So is Cassia a PeVatron? Is Tycho a PeVatron? And in fact, one of the things that we have found is that most likely not, because there is a cutoff in the spectrum. So Cassia spectrum, Tycho spectrum, these have been now measured very, very well by the northern IACTs, and we don't think that these are PeVatrons. Okay, we also study the origins of unidentified hard index. Hard index meaning hard spectral index, which means that the spectrum continues flat quite a way. Okay, so that means there's a lot of TeV emission at high energies. And the 3 of the ones that we're interested in are the Milagro J 2019, there's Milagro J 1908, and then this one, the last one, is actually the Boomerang, which is also a very interesting target. Okay, and then we follow up on ultra high energy gamma sources by detection by Hawk and by LASSO. So what I will do today is just mention a little bit about Boomerang. Ro will talk about 1908, and Julian will talk about LASSO. Okay, so I'm going to skip through some of these slides because we showed them in the colloquium and mention this one. So this is basically the Boomerang region. You can see here, this is a radio map. The red map here is in radio. It's 1420 megahertz. This shows you the historical sort of region. You see here in green is the Boomerang kind of pulsar wind nebula. It's shaped like a boomerang, that's why it's called that. And it has this head region and tail region. The reason, I mean, if you look historically, VERITAS discovered this source in TeV emission. You can see here the VERITAS emission. And what was interesting that came out recently is that this is also a PeVatron in the sense that likely PeVatron candidate was detected by Tibet, it was detected by Hawk, as well as LASSO. Okay, so it's one of the promising PeVatron candidates. And what we did is we studied this source in depth with X-ray instruments to see if we can try to understand the nature of the emission. So I think people here who are experts on MAGIC already know that this was studied well by MAGIC, and MAGIC now sees basically morphology, energy-dependent morphology. So this is the high energy the low energy 0.2 to 1 TeV, and then the high energy is 1 to 6 TeV. And I think right now it's still not clear what is the source of this emission. It could be leptonic, which means that electrons and positrons are accelerated. But if it is leptonic, we would also expect to see X-ray emission, pulsar wind nebula, but we don't see it. So it's not clear, or it could be hadronic, where you have this whole supernova remnant and a molecular cloud, and you could have interactions with the molecular cloud, which then gives rise to TeV gamma rays. So what is important in sources like this is to do a clear, to do a careful study of the energy-dependent morphology as best as we can. Okay. Okay, so what we did is we looked at, so this is work that was done at Columbia with Kayamori and Newstar, and Julian was involved in this, is basically looking at this particular pulsar wind nebula, the Boomerang pulsar wind nebula, and try to get X-ray observations. So here you can see with Newstar, you just go in and look at it very carefully. And in fact, Newstar was able to detect spectrum up to 20 keV in X-rays, and also measure pulsations from this source. And historically, this was studied by Chandra as well. So you can see all the Chandra emission. I think it's hard to see, but you can actually even figure out the torus feature of this pulsar wind nebula. And so Chandra actually resolves the pulsar, the torus jet feature, which probably is the termination shock, the X-ray pulsar wind nebula, as well as the X-rays. Okay. And so you can do with something like this, with detailed X-rays, you can look at the energy-dependent X-ray, and you can do things like, does the profile of the source increase or decrease with X-ray, or is it the same, or does it change? And what we find is if you look at the 3 to 10 keV and the 10 to 20 keV, 10 to 20 meaning the higher energy, it seems like that the image shows that the nebula decreases in size at higher energy, probably due to synchrotron burnout. And we see that the new star spectrum does not show any cutoff and up to 20 keV, suggesting that the maximum particle energies could be 100 TeV. So a lot of work is being done on these sources. So one of the things that we like to do is we try to see if we can do a spectral energy distribution modeling. So this is we use a bunch of models. Basically, one thing you can do is you can, assuming a certain magnetic field and a certain distance, and what we measure with the new star experiment and the upper limits from VERITAS, what is the consistent model that can explain the maximum energy of the particle, consistent with the magnetic field, and what is the age of the supernova remnant? So you can do, you can try to get some physical numbers out of this. Okay, so this is one thing that we are doing now with VERITAS, and maybe I won't get into too much of the details of the modeling because instead refer you to the papers. But what is more interesting perhaps is to talk a little bit about the LASSO PeVatron candidates, because LASSO has now detected, these are actually the LASSO significance maps of the 3 sources that we are studying. One of them is, the first one is the boomerang. You can see that the gamma rays are detected above 25 TeV. And this is from the paper, LASSO paper, the Nature paper. The second source is the Milagro J1908 source that Ro will mention. Again, you can see a very hard spectrum. And the third source is we won't talk about this today, but there's a large number of photons that you detect from above 100 TeV up to 1.4 PeV from these sources. Okay, so maybe Ro, at this point, I should switch to you. And do you want to share your screen? Because the next topic that I was going to discuss is Milagro J1908, which is a very interesting source. And I think I would give you 15 minutes.
Okay, thank you.
Yeah, so why don't you, let me stop sharing. So try to share your screen.
It should work.
All right, I hope you are seeing my slides.
We see it in presenter mode. So we see the 2 slides side by side.
Sorry.
Yeah, perfect. That's great. And can people at the back here, Ro? Okay, go ahead.
Okay, right. So thank you for Reshmi for the introduction. So first I wanted to give you a little background on the source. So this is a very bright source discovered by Milagro. The source has, well, in the units of Crab nebula, it has an emission of 1.4 Crab nebula units at 100 TeV. The source also has an extended morphology with a radius of 0.5 degrees reported by multiple observatories. There are 2 possible candidates responsible for this TeV emission in the region. One of them is this pulsar, middle-aged pulsar located, labeled by this black cross here. The pulsar has an age of about 20,000 years, a EDOT of 3 times 10 to the 36 Earth per second. Another candidate is also a middle-aged SNR that is labeled by this black circle here. If you go to TEFCAT, and you will find that there are dozens of papers have been argued which one of the 2 sources or both of them are responsible for this Milagro J1908 emission. And so today I would like to give you a more comprehensive view from this multi-wavelength gamma ray observation, trying to explain the origin of this source. Okay, so about our data, we used Fermilab data. We also have VERITAS data, and we have HAWK data. So this is a joint collaboration among these between these three observatories. So here I'm going to show you this sky map that we see from the data from these three observatories. The first sky map is in using the Fermilab data with photon energy between 30 to 300 GeV. Again, this black cross is the location of the pulsar, and this blue circle is the location of the middle-aged SNR. And the color map shows you the gamma ray count from the Fermi data. And in the Fermi data, what you see is that the brightest hotspot in this region has an offset from the location of the pulsar, also has an offset from the location of the SNR. However, if you go to higher energy, now we are looking at the sky map from the using the VERITAS data in the energy range between 0.5 TeV to 2 TeV. And now if you compare this sky map to the Fermi sky map, you notice that the hotspot of the gamma emission is now slowly moving toward the location of the pulsar. And if you go to even higher energy, this is above 2 TeV in the VERITAS data. And now you see this hotspot is now a coincidence with the location of the pulsar. We also observed the similar trend this is in the Hawk data. This is the lowest energy range in the Hawk data between 3 to 10 TeV, all the way to above 30 TeV. So in the Hawk data, we also observed this similar trend that as you go to higher and higher energy, you find a more and more concentrated gamma ray emission from the location of the pulsar. So then we put this table together to show you this motion of the gamma ray emission across this wide energy range from 30 GeV all the way to 300 TeV. And the information I want you to pay attention is this last column. This delta is the angular separation between the gamma emission and the location of this middle-aged pulsar J1907. So if you go from lowest energy in Fermi energy, we measure this separation to be 0.3 degree. And then if you continue going to higher and higher energy, you see this delta becomes smaller and smaller. And at highest energy, this separation is now 0.16 degrees. So then we try to build a model. Well, from this table and from the energy-dependent morphology sky maps, we believe that this gamma emission is from the electrons in the pulsar wind nebula created by this pulsar. So why do we see lower energy with larger separation between gamma emission and the location of the pulsar? Is that we think this pulsar might be moving, the proper motion of the pulsar is going from the location of the emission in the Fermi data, and then slowly moving toward its current location. And in the Fermi data, because we are looking at the low energy gamma rays, they are produced by low energy electrons. And so low energy electrons, they have really long cooling time. So we can still see emissions from really old electrons that were produced at the early time, at the birth of the pulsar. However, if you look at the higher energy gamma rays, they are produced by high energy electrons. And high energy electrons, they have very short cooling time. This means if you are looking at high energy gamma ray image, you are looking at more recently, freshly produced electrons. And so this can easily explain this energy-dependent morphology of the gamma emission. So then we try to build a model. This model is saying that the gamma emission we are seeing is from the electrons in the pulsar wind nebula. And we assume there's a fraction, this chi-e says this, the fraction of the total energy in the pulsar wind nebula is stored in the form of electrons. And then there's another component is the magnetic energy with a fraction of chi b. And the energy stored in the electrons, of course, if you know the electron spectrum, then you can just integrate all electrons in the nebula with their energy and then compute the total energy stored in electrons with the magnetic field energy. If you know the magnetic field density, and also if you know the volume of the systems occupying, then you can also compute the total energy stored in the magnetic field. So about these two equations, I would like to say the left-hand side of this equation, this spectrum information and the B field density and the B field volume, these are quantities that we can derive from observations. So for example, if we look at the gamma ray spectrum and we assume a broken power law for the electron spectrum, this broken power law has an energy break, and it also has a cooling index of beta. And then we fit the spectrum to the observed gamma ray spectrum. What we find is that this cooling break happens, well, in the gamma ray energy, the cooling breaks happens at about 2 TeV. And then we converted that to the electron energy that gives us about 17 TeV. And the cooling break index is about 1.4. And we can also try to derive the quantity for the parameters for magnetic energy. So to get magnetic energy, first you need to know the magnetic field density, and this density is connected to the age of the system and also to this energy break in the spectrum. So this break, basically this break is telling you up to above this energy, the electrons are significantly cooled down due to the synchrotron radiation. And then from the observation, we can also know how large the volume this nebula is occupying is basically trying to see how extended this emission is. Well, with a prior knowledge that if you know the distance to the pulsar. So you can see all these parameters, the observed quantities are connected to two important physical parameters. One is the distance to the pulsar, another is the age of the pulsar. So then we can try to come up with a model, assuming that the pulsar is injecting energy into the nebula with this equation. So E dot is the energy coming from the pulsar, and this last term is the adiabatic energy loss due to the expansion of the system. And then we need a boundary condition, that is the current observed E dot is this value. And then we can build a constraint, a model to constrain the age of the system and the B field of the system. That is by requiring these fractions, the sum of the fraction to be 1. And then, so in this map, this is showing you the fraction sum of chi E plus chi B. And for a system that is too young and at a too large distance, you just don't have enough energy to produce the observed gamma ray emission. For a system that is too old and with too small distance, then the pulsar will produce too much energy to overshoot the observed gamma ray flux. So then the system must to live along this diagonal line where chi E plus chi B equals to 1. And then we can use a external information. 10 years ago, there's a Fermi paper made a distance estimation about the pulsar using this dispersion measure. And they reported a distance to the pulsar to be about 3 kiloparsec. So then you can place this 3.2 kiloparsec in this graph, and then you find this intersection between this horizontal line and diagonal line. Then this intersection tells you how old this pulsar is. which is about 22,000 years. And this is not very far from the characteristic age of the pulsar. We also did a little investigation on the hadronic emission, tried to understand if the gamma emission can be explained by this nearby middle-aged SNR, and our conclusion is that in this region, the cloud density, the gas density is just simply too low. And if you think this SNR is a typical SNR that can produce a total energy of 51 erg during its explosion, then this SNR can only explain about 10% of the total gamma emission from this source. So we think it's unlikely for this SNR to produce the gamma emission that we see from the molecular generating array source. So that's basically all from me about this interesting source and our investigation using this multi-wavelength gamma ray observations. So back to you, Reshmi.
Thank you, Ro. Maybe we can stop here just to take some questions in case there are questions on this so far before we move to Julian.
I have a
There's
question.
one from Valenti. Go ahead.
Thank you. If I remember correctly, there was this image with emission from different energies, and the lowest energy was the farthest from the pulsar location. I think it was the Milagro source, the 1908.
Yeah.
And then the intermediate energies were closer, and then the highest energies were more or less next to the pulsar. And you were saying something like the lowest energies, they were more or less located where the pulsar was initially, something like that.
Yeah.
And if it's the case, I was thinking if the pulsar is moving significantly at significant speeds, I would expect that the flow coming from the bow shock of the pulsar wind forming, interacting with the medium, this flow moves away from the pulsar in principle at relatively high velocities. So I would think that this GV emission comes from particles which maybe were injected around the pulsar location not so long ago and were affected there by the pulsar, the shock pulsar flow. Could it be?
Yes, that's a very good question. There is indeed a X-ray paper from a few years ago. They did report, I think they used XMN, and they did observe, well, there's a mild hint of bow shock in front of at this location of the pulsar, but it's not a very strong detection of the bow shock, so they didn't claim a detection, but there is a hint of bow shock around the pulsar.
But would you say that the pulsar, I mean, given that the pulsar location, I don't know, maybe 10,000 years ago or a few thousand years ago was more or less where the GV emission may be, that's a hypothesis. Then you can derive some kind of rough estimate for the velocity of the pulsar, right? So yeah. I mean, my point is that you could try to build a model based on a supersonic pulsar wind nebula moving, in which the GV emission is related to these old electrons, but not electrons that were injected where they are emitting now, but they were accelerated closer to the pulsar location. They are affected, and then they are emitting where they are now, but they have not been there before. They came from the pulsar at some point. So, you know, I mean, an outflow coming from the pulsar with these particles emitting radiation at different energies. The lowest, the farthest, the region, the lowest the energy. I'm not sure it's clear what I'm saying.
Well, I think you are suggesting we can, based on this morphology, we can try to derive the velocity, the proper motion of the pulsar, and then try to see if this pulsar can generate a bow shock. Is that what you are suggesting?
something like this. You can put all the pieces together and try to build a model where you have this dynamics and also the radiation information from the radiation. Yeah, something like that.
So
Yeah,
would you go ahead?
We are working with a theorist group from in Sweden, and well, we didn't try to predict the bow shock, but the theorist is considering this proper motion and diffusion coefficient in the area and the B field, and try to model this energy dependent morphology. And this is an ongoing work, but we can also, well, I don't know if they have this expertise to predict the bow shock, but that's a good suggestion that we can try to do.
Yeah, you can check both approaches, like the diffusive approach and the advection approach from the.
That's a good point. Something to follow up.
Yes.
Paul, there's a question, another question from Paul.
Yeah, about this approach in the X-rays. Isn't there Chandra observations of the region? I mean, detecting the bow shock, the extension of the bow shock, means that the pulsar is not that fast. If you would not detect it, it means that the pulsar is fast. So in this scenario in which this is moving and leaving behind, or diffusing particles as well as they were stating, pressure closer to us, to our times. In both cases, this direction of movement is this, because we're having a look at the XMM bow shock. I mean, it's not really clear that one can derive the proper motion velocity or the velocity itself, but detecting the extended emission of the bow shock itself makes it slow. And this instead, well, there is an arrow there, but if one takes, which is the angular size that has been moved in the precise time scales there, this is how it reads.
So do we know the quality of the XMM data? How good is it? Is it worth asking for more XMM time in the future? But that is a possibility open to us.
52 kilosecond XMM year to date.
Say that again?
52 kilosecond.
52 kiloseconds, okay.
Yeah, I mean, XMM is maybe a little better suited for large, extended.
But do you have radio data on this pulsar wind nebula? Because if you have radio data, maybe you can see the cometary tail, and then you know the proper motion direction of this pulsar.
Yeah.
And I'm not sure if this pulsar is associated with the supernova remnant, this supernova remnant or other supernova remnant. Have you detected any supernova remnant nearby except from this one? Because according to the direction that you showed here, this is not associated with that supernova remnant because it's coming from that way. Right?
Yes, that's right. So did you hear that, Ro?
And it's still it's not a very old pulsar. So it's about 10 to the 4 years, the supernova remnant will dissipate. So you might it's probably that you can detect a supernova remnant in that position.
Did you hear the question?
Yes, well, if I understand correctly, the question is about if we detected the SNR associated with this pulsar in radio band.
Yeah, is there any radio data? And this, is there another supernova remnant? Yeah.
The answer is yes and no. There are radio observations, but there's no detection of SNR associated with this pulsar.
But have you detected any cometary tail?
Any cometary tail? I don't think so.
No.
But if this is the tail structure of this pulsar wind nebula, I have detected some radio data from.
Yeah, well, I think the reason there's no radio detection from this nebula is the reason might be that the B field in the region is quite low. Our estimation of the B field in the region is about 5 microgauss. So it's relatively low B field. That's why you see most of the emission is in the gamma ray produced by inverse Compton scattering, and there's no much emission from synchrotron radiation.
So we take one more question from Jose Maria.
Yeah, the radio observations were from some surveys, or were specific observations with good sensitivity of this region?
For this region.
Yes.
So did you hear that? What are the newest observations that we have of this region?
The newest observation from which?
Radio as well as X-ray, right? Yeah, multi-wavelength, other than gamma rays. Because this is a pretty old source, you know, this was known at the time of Milagro. And it's very close to SS433, about a degree away, I think. So, I mean, in your modeling, you had some other multi-wavelength data, I think.
Right, but that is the gas emission. That is H1, and I have H1 and CO data, but I think the question is about the radio emission from
Radio emission, yes.
from the nebula.
Yeah.
I didn't look into that, to be honest, but I think Meerkat might be able to cover this region. So maybe we should check with Meerkat.
Yeah. Okay, I think though we should move on because we don't want to run out of time, and I know that Julian needs 10 minutes. So Julian, you should share your slides.
Yes, I'll share my slides.
I don't see your slides yet.
Yes, let me start the slideshow. Do you see my slides now?
Yep.
All right,
Go ahead.
so yes, so Reshmi has already introduced the cosmic ray and our scientific motivation for studying PeVatrons, but I'm just including this plot again. And when we study the cosmic rays, just like any other astrophysical questions, if we start by writing down the Fokker-Planck transport equation, then we lay out these terms of cosmic ray processes like injection, diffusion, and energy loss. These are all relevant to the cosmic ray spectrum. And these processes are relevant with the physical properties like shock speed, magnetic field, ambient matter and photon density, diffusion coefficient. These properties are all sort of embodied in the cosmic ray spectrum from each source. And also, like Reshmi mentioned, in the neutral byproduct particle spectrum, like photons and neutrinos. So if we want to study the galactic PeVatrons, we in particular focus on the hard X-ray and very high energy and ultra energy gamma rays. So when we look at the current instruments, there's LASSO, as Reshmi introduced, which reported a lot of ultra energy sources along the galactic plane. And there's Hawk and Tibet AS Gamma as well, covering a similar energy band. And right below the ultra high energy band, we have IACTs like VERITAS, MAGIC, and HESS, which have a strong resolving power, like you can see here in this plot, with a white dashed line being Hawk contour of energetic source VERITAS J2019 plus 36.7. This source was a single extended source by Hawk, but VERITAS was able to resolve this into two individual sources. And by introducing X-ray telescopes, such as New Star in the hard X-ray band and Chandra and XMM in the soft X-ray band, we have even better resolving power, however, for a smaller region. So we can focus on, for example, this one particular very high energy source and resolve the central engine, which is a pulsar in this case, and grab the whole emission from the extended pulsar wind nebula and extract the physical properties, like I mentioned, magnetic field, cosmic ray electrons and positron spectrum, maximum energy, things like that.
Sorry.
So this use multiple instrument has 1 million sources reported and about a slightly
Julian, you're cutting out a bit.
Maybe she should switch
has
off camera.
I think you're cutting out a bit. Turn
Yeah,
off
let
your
me
video.
turn
Yeah,
off my video.
yeah, better.
Is it better? Okay, all right. So that's how we use multi-wavelength instruments to study galactic PeVatrons. And when we go back to the LASSO catalog, out of 90 sources, about 50 of them have a known cosmic ray accelerators, meaning there are possibly associated other wavelength sources such as PWN or TV halo, SNR, or young massive star clusters, things like that. However, nearly half of it, 40 out of 9 sources, have no counterpart or multiple counterparts that one cannot determine which cosmic ray accelerators is generating this ultra energy or very energy gamma rays. There are several possibilities. It could be that there is a known accelerator but hasn't been observed yet, or it is very faint that is not observed by the current instruments. Or it could be some molecular clouds, for example, illuminated by cosmic rays from nearby accelerators that is away from this gamma ray source. Or maybe it's a totally new source types of cosmic ray accelerators. So to study this, to find out what is actually accelerating the cosmic rays, we use multi-wavelength instrument, including VERITAS, HAWK, Fermilab, and XMM Newton. So these 3 are among the LASSO dark PeVatrons, which have no or multiple counterparts. And I will cover J20-108 plus 5157 on the left, and LASSO J0621 plus 37 plus 55 on the right. So LASSO J20-108 plus 5157. This one is very famous source, having a very hard spectrum, very bright in the ultra energy band, and a very sharp, oddly sharp peak in the gamma ray, TV gamma ray band. It's highly significant above even 100 TV and marginally extended or even point-like in both WCDA and KM2A energy band, so above 1 TV. There are molecular clouds and young star clusters. So you can see here, young star clusters near the region, which could make you think that this might be a hadronic accelerator. However, there's also an unidentified Fermilab source, only 5 arc-minute away, which shows a pulsar-like sort of spectrum, which sharply cuts off below 10 GeV. We observed this source with VERITAS. We have 35 hours of exposure, and we did not detect the source. HAWK did detect the source, and XMM Newton did not detect any point or extended emission in this region. We did not detect any extended emission around the Fermilab source either. So we performed SCD modeling using 2 different cases, one for a leptonic case, where it might be a mini pulsar halo, showing this pulsar-like spectrum being a pulsar and the inverse Compton spectrum and synchrotron spectrum with a very low magnetic field around 1 microgauss. We also tried to model this as an SNR embedded in a molecular cloud and illuminating the molecular cloud with a cosmic rays accelerated at the SNR. But clearly this cannot explain the Fermi LAD source. This might be background pulsar unrelevant, and it could be a molecular SNR combo because a very high energy spectrum is just well explained by both cases. So this is a truly unidentified source still. When we look at the LASSO J 0621 plus 3755, this is a pulsar halo candidate. It is not detected above 100 TeV, so this is not an alternative source. It is very largely extended with a radius of 1 degree in LASSO energy band, so from 1 TeV. So this poses a lot of challenges in VERITAS analysis because the field of view of VERITAS is 1.75 degree in radius. So this is comparable to the source extension. Then background estimation becomes a big challenge. So here in this study, I used a field of view technique, which is to estimate the background using everything outside of the source extraction region, which is marked here as a circle with radius 1 degree. So to do that, we have a very accurately estimated acceptance map because we're basically rescaling the acceptance map using these counts, off counts, to estimate the background on the on region. So I also developed a technique to generate a 3D acceptance map, which is shown here. It is very interesting for its own sake. It's in the lowest energy band to the highest energy band from 0.3 to 10 TeV. We see how elevation and azimuth of the observations, the observing conditions, and the energy could affect the acceptance of the telescopes. And you definitely see the energy dependent and radial asymmetry in the acceptance map. So this precisely measured acceptance map is applied to estimate the background of this largely extended source. Even with 40 hours of exposure, we did not detect the source. And XMM Newton data also did not show any emission associated with this source. However, we did detect the pulsar for the first time in the X-ray band. So stay tuned, we're preparing the paper. And also we're modeling the pulsar halo using a diffusion model, theoretical model. Here you're seeing the LASSO spectrum from the KM2A and WCDA and the VERITAS upper limits from 2 different analysis softwares. This lies above the LASSO catalog spectrum. This is not the only case. We, as a community, may want to discuss this at some point. WCDA spectrum tends to be pretty away or deviate pretty much from the KM2A spectrum, even in the overlapping energy band. And it often gives a very sharp, oddly sharp peak. So it's really difficult to model it theoretically using any kind of, physical assumptions. So this is something that we can discuss as a community. this is just table comparing this source, LASSO J0621, and the other two old pulsars, Geminga and Monogem. This pulsar is a gamma ray pulsar, now also an X-ray pulsar, with a similar spin-down luminosity to other old pulsars with halo detected. It might be much farther than these two sources, Geminga and Monogem. That's why the source extension is pretty small, or still large, but smaller compared with other pulsar halos. So that's it. This is what we study using VERITAS, also dark PeVatrons.
Thanks, Julia. Questions?
Yeah, just a comment about these spectral differences in between WCDA and KM2. Well, this is not the only source, right?
Yes, correct.
And in other cases, in this particular one, the spectrum at the highest energies, this red thin line, there are statistical errors in the bow tie, which is much thinner than the one reported in the first paper, Aharonian 2021, for the same instrument. Right?
Yes.
Is it just a fit to the red squares? Red crosses?
No. So looking at this, oh, you mean this one?
Yeah.
No. So this one, actually the label is wrong, I think. So this purple and the data points should go together. They are from the Aharonian paper. And this line, the red line, is from the catalog.
So the red crosses should be purple crosses?
Yes, correct.
Yeah, it makes more sense.
Yes.
To be honest, the color is different. You know, it looks purple to me.
Yes, it's difficult to tell. Yeah, I should change the color.
Yeah.
Yes, this has a
first-
small error, I think, because it just added more data.
And also for the previous source, 2008, you were showing Hawk results, the detection.
Yes.
How much data, which is the energy range?
It's the same source, by the way. LASSO, that's the LASSO catalog name is LASSO J2106.
Yes.
But we are,
21.
is it the
wait.
same source or different source?
No, those are
No,
different.
this is different source.
Okay.
This is actually, yeah, LSD observed this.
Yes.
This source, and also placing constraining upper limits in the and there was also the non-detection. We reported also non-detection in XMM. But is this Hawk data results? Do you know which energy range are they covering and how much data they got to get this?
Yeah. Yes, this is 2,400 days of data. And the energy range is from a few TeV to about 100 TeV.
So it's overlapping partially with the VERITAS.
Yes. Yes, correct. So that was another sort of concern. We're not really showing the catalog, LASSO catalog result here, but the WCDA result doesn't quite match with the Hawk data.
Yeah. And the sensitivity of Hawk and VERITAS in the overlapping energy range, shouldn't it make VERITAS to detect it as well?
That's a point. So I think, well, we think for now the exposure might be not long enough, but also the high energy sensitivity that overlaps with Hawk is not as good right now. We're developing the high energy particular analysis technique right now. So I'm not sure if I can say much about it here, but you may hear from us soon. We have some news about it.
Okay.
If there are no other questions, then I think we can close this here. And I think people here locally can always talk to me, I'm around. And I just want to thank Julian and Ro for joining.
Thank you so
and
much
we-
for the opportunity.
Thank you.
Yeah,
Thank you very much.
okay,
Thanks a lot.
bye. This was an experimental opportunity, I hope that was okay.
I just stopped the.
Yeah, that's fine.
So Reshmi, which are the plans for